So, in the last couple of classes, we discussed extensively the internal interaction parameters, especially chemical shifts and coupling constant. Coupling constant, I gave lot of information for you about how do we get the multiplicity pattern, how do you give the nomenclature for a different multiplicity pattern for a particular proton when it is coupled to single proton, double proton, 2 protons, 3 protons, a chemically inequivalent or chemically coupled to chemically equivalent group of protons, and we accordingly gave a nomenclature like doublet, triplet, quartets, varieties of things, and we took a realistic example and get the information about what is the pattern we are going to get. We discussed a lot about those things, and at the same time I gave you strength of J couplings, information about the strength of J coupling. One bond coupling is quite larger, especially in hydrogen molecule. As the number of consecutive bonds keep on increasing between two interacting spins, J coupling keeps reducing. That is a general trend. But I gave several examples where J coupling can be extended even up to 5 bonds, 6 bonds, 8 bonds, 9 bonds also. They are all rare examples, but not always true. But remember, this is a general guideline. J coupling decreases with the increase in the number of consecutive bonds between two protons or between two interacting spins. But there are exceptions like this, especially in the linear molecules or molecules in zigzag fashion. This type of coupling strength can be observed. Significant coupling strength can be observed. Further, I said what I measured the coupling of in a hypothetical molecule of a triplet and a quartet in a given magnetic field at 200 megahertz. The same thing when I measured at 400 megahertz, I showed you the coupling remains invariant with the magnetic field, whereas the chemical shift linearly changes, but coupling will not change. So, coupling is always constant in any spectrometer you measure, whereas chemical shift linearly changes. This is what we discussed a lot, several things for several classes. We have been discussing about chemical shift and J coupling. This information is needed for you if you want to take a deep plunge into NMR analysis of varieties of molecular to take it further into your research. So, with this today we will continue further and see how we can analyze the spectrum of given molecules. Okay. But remember, when analysis of the spectrum there are two ways. One, characterization of the molecule. I give you NMR spectrum, you look at the peak and say, hey, there is a CH3 group here, benzene group here, CH2 is there, my molecule is having a phenyl group CH3 and CH2, fine. That is one way of doing, because your idea is only to characterize the molecule. But if you really want to get the conformation information, if you want to get the structural information, then you have to really analyze the multiplicity pattern and complete information, including the intensity pattern of the lines is needed. Only then analysis will be complete to get more information about the given molecule. So, that is another way of analysis for which we need to understand what is called a spin system. So, today we will start understanding spin systems and Pople notation. When I say I have to analyze the spectrum, generally they are all coupled spin system. I told you they are all coupled spins. If you uncoupled, you get only single peak, then there is no interest to analyze. But if you want to analyze the spectrum, as you know, the spins are coupled among themselves. In this, what is a coupled spin system? What do you mean by a coupled spin system? Let us consider the group of spins like this 1, 2, 3, 4 and 5 there are 5 different protons. You can think of coupling between 1 and 2, coupling between 1 and 3, 1 and 4, 1, 5, 2, 5, 3, 5, 4, 5, all coupling you can see. For example, coupling between 1 and 5 can be 0, no problem, but it is a part of the coupled spin system. This is called, these 5 protons are called coupled spin system. There exists coupling among themselves. Among all the 5 protons there is an interaction. Interaction strength of one of them could be 0. One coupling 1 3 could be 0 or 1 5 could be 0, does not matter, but it forms part of the coupled spin system, and these are all called coupled spin systems. In NMR we say coupled spin system means they are part of this group, they are coupled, there is a coupling among themselves. And if there is another group here and there may not be coupling between this and this, then this is one spin system, this is another spin system. There can be many spin systems possible, many spin systems can be present in the molecule. Okay. So, this is the important concept to understand what is a coupled spin system. Coupled spin system is a group of coupled spins with varieties of coupling strengths, different coupling strengths could be there, or it could, one of them could be 0, does not matter, but spins must be a part of the coupled group of spins, coupled spin system. And then spin system can be classified into two groups. One is, when I say, for example, this is just to give you an idea about what is a spin system before going further. For a hypothetical molecule, I take it. There is a coupling between this and this CH3 group, maybe or may not be, does not matter. There is a coupling between this proton to this proton, fine, but there is no coupling between this proton to this proton, because in between there is a break in the coupling strength, and this forms one coupled spin system, this form another coupled spin system. This is one coupled spin system, this is another coupled spin system. So, in a given molecule there can be n number of coupled spin systems. This is very important when you want to understand 2D NMR like Toxi. When I go further, I will discuss these things. So, in the spin systems, this is a part of a coupled group of spin system, this is a part of coupled group of spin system, whereas between these two there is no coupling. So, there are two spin systems in this molecule. The coupled spin systems can be classified into two groups. What are those two groups? One, I will say they are strongly coupled and weakly coupled. What do you mean by weakly coupled? What do you mean by a strongly coupled spin system? This is something which is we have to understand. What do you mean by weakly coupled and strongly coupled? Of course, you from your knowledge you can say if the interaction strength but J coupling is larger, coupling is stronger, interaction strength is larger, and we say coupling is very small, it is weakly coupled. That is common belief we can say, but that is not the only way to understand. The way to understand whether the two protons are coupled, which is strongly coupled or weakly coupled by different way. One is you have to measure the chemical shift difference between the two coupled spins and measure the J coupling. If the chemical shift difference between two coupled spins is very large compared to coupling strength, then it is called weakly coupled spins. Remember, you consider the example of two spins, two different chemical shifts, one here, measure the difference in the chemical shifts, and that delta difference in two chemical shifts of these coupled spins is very large compared to the coupling strength, which is let us say doublet of doublet, in which case these spins are called weakly coupled. On the other hand, and of course, we can find out what is the condition for that weakly coupled. J by delta is should be extremely smaller than 1, very smaller than 1. That means this is large. When this separation is very large, this is the condition, then J by delta is very small, of the order of 0.01, 0.1001 lie will be there. Then smaller this value, it is more and more weakly coupled. On the other hand, in the case of the strongly coupled, the chemical shift difference delta between two coupled spins is less than or equal to, or at times approximately equal to coupling constant itself. Then such spins are called strongly coupled spins. Please remember, when the chemical shift difference between two coupled spins is sufficiently larger than J coupling, where the parameter J by delta is very smaller than 1, then it is called weakly coupled, whereas in this case when the chemical shift difference is approximately equal to J or very much smaller than J, in the condition J by delta in this case is approximately equal to or greater than 1, then it is called strongly coupled spin system. This is the way we have to classify the spin system. Then you may ask me a question, so what? How does it matter for us? The way the spins are weakly coupled or strongly coupled defines the type of spectrum you get. The spectrum for strongly coupled will be different than the consider two example of two protons. If they are weakly coupled, you get one type of spectrum. If they are strongly coupled, you get another type of spectrum. Both are two protons only coupled between themselves, but the type of spectrum you see is different. That depends upon coupling strength and chemical shift difference. So, this is an example of the weakly coupled simple spectrum I am showing you here. Here I have taken the example of two coupled spin system A and X, it is called AX spin system. This is the chemical shift of A, this is the chemical shift of X, it is a doublet that we have been seeing already. I explained to you this separation is larger, this is J coupling, and now measure the separation between this and this chemical shift of A and chemical shift of X you can measure, and measure the difference delta A minus delta X, and if this is very larger than this is the type of pattern you are going to get. This is called a weakly coupled spin system. This is two protons are weakly coupled here, provided this coupling is this separation this delta A minus delta X is very larger than this coupling J coupling. This is what is important thing. See, chemical shift difference is this is a weakly coupled spin of two coupled protons, two weakly coupled spectrum appears like this. What are the weakly coupled keys? This is the general rule. Remember, delta by J should be very much greater than 1, or if you take the reverse of that, J over delta this should be very much smaller than 1. Usually, it is not always the case. General convention is if chemical shift difference over delta over J is larger 50 times more. For example, I measure the delta difference between two protons, chemical shift difference, and also measure the J coupling, divide one by other, and if this value is more than 50, this ratio, then it is weakly coupled. You take the reverse of that. If I take J coupling over chemical shift difference, if I take the divide the J coupling by difference in chemical shift, if this value is much smaller of the order of 0.01 or 0.02 or even smaller, they are called weakly coupled spins. So, this is the condition for that. Homonuclear weakly coupled spins, I will give you an example like this. This is a molecule, simple molecule, we have two protons I and J. What is the J coupling between this and this? It has already been measured around 2.9 hertz. Let us say you are measuring, you take the spectrum of this in a 500 megahertz spectrometer, 3.75 ppm, take 4 for calculation, 4 into 4 ppm in 500 megahertz is 2000 hertz, and this is 2.9 hertz. 2.9 or 3 by 2000 if you take, this is much smaller than 1. Obviously, it is a weakly coupled spin system, because the coupling here is much smaller than the chemical shift difference between these two protons. This is one example of weakly coupled spin system. Take another example like this. This proton and this proton coupling is about 5.6 hertz, and let us say same 500 megahertz, this is 1 ppm, let us say 500 hertz, 5.6 over 500, see almost 100 times smaller, is 0.01, ratio is 0.01, very small. So, this is also weakly coupled. So, if you want to find out either strongly coupled or weakly coupled, then it is going to be J over delta difference you have to calculate and find out its ratio, and this one above 500 megahertz and above, this is weakly coupled, even 100 megahertz itself this weakly coupled. Why I am telling frequency of the spectrometer here? As I told you, chemical shift difference linearly varies with the magnetic field. The same weakly coupled or strongly coupled, if I go to very high magnetic field, because the chemical shift difference becomes larger, it may become weakly coupled. Remember, strongly coupled will become weakly coupled at a very high magnetic field strength, because chemical shift difference becomes larger, or weakly coupled at a very high magnetic field can become strongly coupled at low magnetic field. This is the important thing you should remember. Take an example of a molecule like this. This is heteronuclear coupled, fluorine and proton in these two systems. The question is, are they weakly coupled? Are they strongly coupled? Remember, you are looking at the heteronuclei, fluorine and proton. If I take a let us say 500 megahertz spectrometer, if I take 500 megahertz spectrometer, proton comes at 500 megahertz. Where does fluorine come? Fluorine will resonate at, let us say, 470 megahertz. What is the difference between them? 30 megahertz. That means the chemical difference is 30 megahertz, whereas this coupling is of the order of 10 hertz or 15 hertz. That is all, very small value, whereas chemical shift separation is 30 megahertz, 30 into 10 to the power of 6. Huge separation in the chemical shift. Megahertz, the resonating frequency is nothing but the chemical shift, because that is where you are looking at the, and of course, I already discussed with you, chemical shift is the difference between the resonant frequency of the reference with respect to your peak divided by the spectrometer frequency. So, this is spectrometer frequency difference is 30 megahertz. That means heteronuclear coupled spins are always weakly coupled. Remember this point, heteronuclear coupled spins are always weakly coupled, because the chemical shift separation is of the order of several megahertz. That is weakly coupled spin system. So, heteronuclear cannot be strongly coupled. What happened in a labeled molecule? For example, I consider a molecule like this. 2 carbons are labeled. Labeled means enriched. Abundance is 1.1%. Somehow after labeling it is 100% abundance. When there is 100% abundance, there is a coupling between carbon and carbon. Do not worry about it. Proton I am decoupling. I will tell you what is decoupling, everything later. I do not bring in the coupling of proton to carbon. I see only carbon carbon coupling. Carbon carbon coupling is 67 hertz, one bond, very large. But look at the chemical shift, 141 ppm. Even if you take, let us say 400 megahertz proton spectrometer, 100 megahertz is the resonating frequency of carbon. 100 into 141, see it is 14,100. Where is the chemical shift separation? And this is only 67. So, it is a weakly coupled. So, even in a labeled system, homonuclear coupling is so small and chemical shift separation is so large, this can be a weakly coupled spin system. We will go to the other example like this. Here heteronuclei, again nitrogen 15 and carbon 13 are labeled. I am removing the coupling with proton, consider only coupling of carbon with nitrogen, and the coupling between carbon and nitrogen is 14 hertz. That is all. But what is the resonating frequency? If I take 100 megahertz, 400 megahertz, carbon is 100 megahertz, nitrogen 15 resonates at 40 megahertz, because J is gamma is 10 times smaller. I told you gamma of nitrogen is 10 times smaller compared to proton. Carbon 13 gamma is 4 times smaller compared to proton. So, resonating frequency of nitrogen 15 in a 400 megahertz spectrometer is 40 megahertz, whereas carbon is 100 megahertz. So, what is the difference then? 100 minus 40, 60 megahertz is the difference. So, a chemical shift difference is 60 megahertz, whereas coupling is only 14 hertz. This is an example where heteronuclear spins, even when they are labeled like this, they are weakly coupled. This is a classic example of a heteronuclear weakly coupled spin system in the labeled molecules like carbon 13 and nitrogen 15, both are labeled. Now, we will go to the example of strongly coupled spins. So far we discussed about weakly coupled. Let us take the example of strongly coupled spins. I told you the definition already. The requirement for spins to be strongly coupled, if I have to say they are strongly coupled, the chemical shift difference between them must be very much smaller than the coupling constant between them, or at the most of the order of coupling. That is what the condition I put in. Then they are strongly coupled. So, go back to the same equations. J by delta delta earlier in the other case should be very much smaller than 1, but in this strongly coupled case it should be greater than 1. Whereas, if you take the reverse of it, chemical shift over J in the weakly coupled case, I said it should be very much larger than 1, but it should be very much smaller than 1. The reverse of it is a strongly coupled case. You understand? Chemical shift difference between 2 coupled spins, if you measure that and take the coupling constant, take the ratio of the chemical shift difference over the J coupling, if you take that ratio, it should be very much smaller than 1, then they are strongly coupled. Of course, you can take the other way, measure the coupling and divide by the chemical shift difference, that then it should be larger than 1. This is the condition for the nuclear spins to be strongly coupled. Then I say these nuclear spins are strongly coupled. Two strongly coupled spin case, I will tell you what is A, B, AX, everything today itself as you go ahead further. A spectrum of a strongly coupled, two protons coupled is like this. Do you find the difference? What did we see in the weakly coupled case? Two lines of equal intensity. 4 lines we got, all were equal intensity. I gave you an example of a two protons A and X coupled, just couple of slides back I showed you for a weakly coupled example. This is chemical shift of A and this is chemical shift of X, this is JAX, and we got, and I said it is a weakly coupled 2 spin case. But look at the strongly coupled. What is the difference you see? The central lines are more intense than outer lines. Of course, these two lines are of equal intensity, these two lines are of equal intensity, identical intensity, but between central line and the outer lines intensity there is enormous difference. Not only that, it can be so happens and it can be even more large as, and outer lines can be even more weaker. That depends upon the ratio of chemical shift difference over J coupling. What is that value? If it becomes smaller and smaller and smaller, then the pattern keeps changing. Not only that, the intensity pattern keeps changing. You understand the difference now. The strongly coupled case, same 2 spin if I consider, the spectrum is completely different. What you see for weakly coupled and strongly coupled are different. But remember, in the strongly coupled case, you cannot analyze the spectrum so easily. All peaks are not of uniform intensity, and just like you did for the example of the weakly coupled, I measure this chemical shift of A, I measure the center chemical shift of X, and I measure this separation, I get the coupling constant. This is called straightforward analysis, that is called a first order analysis, that is easy in the weakly coupled case. But in the strongly coupled case, this way of first order analysis is not possible. You cannot analyze. Strongly coupled case, an example is like this. There are 2 protons here, this and this. For example, 2 carbons here coupled. This proton-proton coupling is 1.6 hertz and chemical shift difference is 4 hertz, you see, very small value. Even if you go to 500 megahertz, it is only 10 hertz. If you take the delta delta or J over delta, if you take 1.6 or 10 hertz, this is not small, very much smaller than 0.001. That is what we should get for weakly coupled. It is very large value. They are almost comparable. J coupling and chemical shift separation here and here almost comparable. That is why they are strongly coupled. Even at 500 megahertz, this molecule, these 2 protons are strongly coupled. The 2 protons are strongly coupled in both the molecule. Now, if you consider this one, I will not bother about carbon 13, of course, carbon 13 we showed in the previous example. Now, I consider the protons here. Here 2 protons if you consider, they are not equivalent, they are different, chemical shift difference is there. But then the J coupling is much smaller and the chemical shift separation is also much smaller. In this example also I did not give the values here, but this is also strongly coupled. These 2 protons are also strongly coupled like here. And again these 2 protons gives like a spectrum which are of different intensity. They are not of, all the peaks are not of equal intensities. So, this is what I wanted to tell you about Pople strong and weakly coupled spin system. Okay. If you carefully observe, if you have understood already, I use certain nomenclature. When I was talking about weakly coupled 2 protons, I used the letter A and X. I said AX spin system, if you have noticed it. When I was discussing about strongly coupled spin case, I used the letter A and B. I did not use A and X. There is a reason for it. Always we have to mention weakly coupled and strongly coupled by a certain method. There is a method for it. You can't write AB and say it is weakly coupled. You can't write AX and say it is strongly coupled. No, that is not possible. There is a notation, there is a way we can say the spins are strongly coupled or weakly coupled. This is what is called Pople notation. I told you, you have to understand this. If you know the Pople notation, you know whether the spectrum, when you are analyzing, you say whether the spins are strongly coupled or spins are weakly coupled. And how do we put a nomenclature for this is like this. Each spin half nucleus of a coupled spin system, I am talking about spin half nuclei, I am not worried about spin 1, we will discuss that later. Spin half nucleus of the coupled spin system is assigned a Roman alphabet. What is a Roman alphabet? Like it A, B, C, D, E, F, G up to X, up to X, Y, Z. All 26 characters you can consider. And then each proton or group of protons is given a letter. And then for a weakly coupled spin system, the letters are assigned that are far away in the alphabet order. Look at this one, A and X, I put it. X is far away from A in the alphabet order. That means they are weakly coupled. For weakly coupled, the letters should be far away in the alphabet order. If I put A and B, the letter is immediately next to that. That is strongly coupled. So, for weakly coupled, the letters to be assigned are far away in the alphabet order, and such type of spectra are called first order spectrum. The spectra what you are going to get are first order. First order means straightforward analysis is possible. Straightforward analysis is possible for weakly coupled. That means looking at the spectrum, I can measure the chemical shades and coupling constant fairly easily without going into more complications. Whereas the strongly coupled case, the spins are assigned letters that are very close in the alphabet order. For example, here if you go here, AB is strongly coupled, ABC is strongly coupled. Here A and X is weakly coupled, M and X if you consider, that is also weakly coupled, because M is far away from A and X is far away from M, and A and X are again far away, they are weakly coupled. AB is strongly coupled, ABC is strongly coupled, like this. So, this is how you have to put a nomenclature for the coupled spin system. First order and second, weakly coupled gives you first order spectrum, straightforward analysis is possible, and strongly coupled spectra are called second order. There is no way you can analyze in the straightforward way. You have to use quantum mechanical calculations. Although I showed you simple 2 spin case, we get like this 4 line pattern with 2 lines of central intensity, set 2 central lines of higher intensity than 2 outer lines. But then even the intensity you have to calculate, it is not easy. You have to do some mathematical analysis you have to do. So, the second order spectra are not easy to analyze. You have to do quantum mechanical calculations or numerical simulations you have to do. So, that is the thing you must understand for strongly coupled and weakly coupled spin system. How do you put the letters? And this is called Pople nomenclature. The nomenclature is very simple to analyze. What are the nomenclatures you can think of for weakly coupled spins? If you have 2 weakly coupled protons, it can be AX. If there are 3 weakly coupled protons, we can call it AMX, 4 weakly coupled protons, AMPX, etc. And in general, as I said, spectrum of even for AX spin system, 4 lines we can analyze, AMX 12 lines we can analyze, AMPX gives you 16 lines, we can easily analyze, not difference at all. Okay? No, sorry, not 60, AMPX 2 cube into 8 into 4, 32 lines, that is also easy to analyze, very easy. Straightforward analysis gives you chemical shift and coupling constant, no difficulty, we can easily analyze it. Weakly coupled 3 spins, for example, is like this, A, M and X. Here, because of different substitutions here, the chemical shift of all the 3 are entirely different. One is here, other is here, other is here, very well separated peaks. Each of them will be split because of A is split because of M and X, you will give 4 line pattern. This gives 4 line pattern, this gives 4 line pattern. But remember, they are far away separated. This is far away separated from this is far away separated from this, and these 2 are further separated far away. In an example like this, in this molecule, these 3 protons form weakly coupled AMX spin system because 3 protons, homonuclear weakly coupled spin system. This also, for example, in this case I have taken 3 examples, 3 protons coupled among themselves, 3 nuclei, A, M and X. A is proton, M is carbon, F is fluorine. Of course, all the 3 heteronuclei, I already told you the resonating frequencies are separated by several megahertz. As a consequence, heteronuclei are always weakly coupled. When I say this proton, carbon and fluorine coupled among themselves, 3 protons, invariably you do not have to worry about it, you can call it AMX spin system, weakly coupled. So, it is a heteronuclear 3 spin weakly coupled, it is a homonuclear 3 spin weakly coupled, but the main condition for either of them is chemical shift separation should be very much larger than the J coupling. That is what we are seeing in both the example. So, if you go to the nomenclature for a strongly coupled spin system, how do we give the nomenclature? We say AB, ABC, ABCD, etc. And spectrum of strongly coupled spins cannot be analyzed by first order methods, I told you. Already I showed you the peaks are of not identical intensity, there will be different intensity. And chemical shifts cannot be obtained easily, individual chemical shifts you do not get, you can only get the difference of chemical shifts. I know what is the difference between chemical shift of A and B, but I do not know the chemical shift of A, I do not know the chemical shift of B. It is not possible to obtain. So, for a simple example of a strongly coupled spin in this molecule, these 4 protons are strongly coupled called ABCD. This is another example ABCD, strongly coupled. All the 4 protons here are strongly coupled because the chemical shift separation among themselves are much smaller compared to J coupling. So, this is how all the protons here are strongly coupled. Okay, now this is for the individual protons, both are individual heteronuclei, how we can give nomenclature for homonuclear and heteronuclear spin, both weakly coupled and strongly coupled, fine. So, you can ask me a question, what happens if there is a chemical equivalence, what happens if there is magnetic equivalence, what happens if there are groups of peaks like CH2, CH3 group, how do you put the nomenclature for that, how does that NMR spectrum come, there is a way to understand. There is a nomenclature for that also. We will come to that later, we will discuss, that is a extensive discussion we can do, but at the moment this is the time is getting over, I am going to stop here. Today I introduced to you about what is a spin system, what is a coupled group of spin system. I said there can be n number of protons coupled among themselves, n number of nuclei, both homo and heteronuclei can be coupled among themselves, that is form a coupled spin system. One of the coupling can be 0, does not matter, but there must be, it must be a part of the coupled spin system. If you consider 3 protons 1, 2 and 3, 1, 2, 1, 3, 1, 3 are coupled, one of the coupling may be 0, but there could be 1, 3 coupling may be there, 1, 2 may be 0, but there is a part of the system because 2, 3 coupling is still there, 1, 3 coupling is there. So, that is a coupled spin system. The coupled spin system can be divided into 2 groups, classified into 2 groups, strongly coupled and weakly coupled. Weakly coupled is the one where chemical shift separation is larger than the coupling constant. Strongly coupled is one, chemical shift separation is smaller, almost equal to coupling, J coupling between the interacting spins. So, and then weakly coupled I said easy to analyze, straightforward analysis is easy, all the lanes are of equal intensity, split all the multiplicity lines which are split because of various couplings. Whereas in the strongly coupled case all the peaks are not of equal intensity, and strongly coupled case cannot be analyzed in the first order way. In the strongly coupled case you cannot get the chemical shifts, individual chemical shifts, many times you can get only the difference in chemical shifts. Whereas in the weakly coupled case chemical shifts and J coupling can be obtained in a straightforward manner, very easy. And I said nomenclature for the weakly coupled is the letter A2 which is far away in the alphabet order, in the Roman alphabet. Each spin off nuclei is given a Roman alphabet, and weakly coupled means the letter should be far away in the alphabet order. Strongly coupled means the letters should be close to each other. AB, ABC, ABCD, there are strongly coupled spins. AX, MPX, MPX, they are all weakly coupled spin system. So, I took the example of couple of molecules to show you how the chemical shift separation will be there, how the J coupling between them are there, how they are strongly coupled or weakly coupled that we discussed. We understood whether in given example whether the spins are strongly coupled or weakly coupled. So, with this I am going to stop here with this Pople nomenclature I have given you. We will continue with the Pople nomenclature and type of spectra we get for strong and weakly coupled case when we have chemical equivalence, when the group of equivalent spins etc. in the next class. So, thank you very much.